CS 407, Numerical Analysis, Section 7.4, Methods for First and Higher Order Systems. So far, we've restricted ourselves to single differential equations of the first order, with accompanying auxiliary conditions. For most of you, that's probably enough, but scientific and technical problems often have a lot more complicated situations. Next to your complications that occurs is with systems with several first-order equations. For example, the Sun and 9 planets form a system of particles moving under the jurisdictions of Newton's laws of gravitation. Position vectors of the planets constitute a system of 27 functions, and Newtonian laws of motion can be written then as a system of 54 first-order ordinary differential equations. In principle, the past and future positions of the planets can be obtained by solving these equations numerically. Well, let's look at something a little bit more modest. Consider two differential equations with two auxiliary conditions here. X prime is equal to x of t minus y of t plus 2t minus t squared minus t cubed, and y prime of t is equal to x of t plus y of t minus 4t squared plus t cubed, with initial conditions x0 equals 1 and y0 equals 0. This is an example of an initial value problem that involves a system of two first-order differential equations. Notice in the example given, it's not possible to solve either of the two differential equations by itself, because the first equation governing x prime of t involves the unknown function y, and the second equation governing y prime of t involves the unknown function x. In this situation, we say the two differential equations are coupled. The analytic solution to this can actually be solved, and in the second bullet we have the analytic solution. The authors of the text invite the interested reader to verify the analytical solution. Unfortunately, I had a prior engagement tonight, so I had to decline their invitation. It's still open to you, although I'm certain you're quite busy as well. Instead, let's take a look at a simpler example. So, consider these two differential equations. X prime of t is equal to x of t plus 2t minus t squared minus t cubed, and y prime of t is equal to y of t minus 4t squared plus t cubed. Initial conditions are x0 equals 0 and y0 equals 0. Now, this is superficially similar to the previous example, but it's actually a bit simpler. These two equations are not coupled, and they can be solved separately as two unrelated initial value problems. Naturally, our concern here is with the systems that are coupled, since the methods that solve coupled systems can also solve those that are not. This procedure extends to systems whether they're coupled or uncoupled. So, in other words, if we solve the coupled problem, we can solve the uncoupled problem. One method we can use for solving these is we can use the Taylor series method to solve the coupled equations. We begin basically by differentiating the equations that constitute it, like we did in section 7.1 of this text, and here we get x prime is equal to x minus y plus 2t minus t squared minus t cubed. Y prime is equal to x plus y minus 4t squared plus t cubed, and we follow this on with some more differentiation. Of course, it involves more differentiation and Taylor series. Once we do the derivatives, say up to the fifth order, then we can write a program to proceed from x of t to x of t plus h, and from y of t to y of t plus h, using the first few terms of the Taylor series, say up to the fifth term. Here x and y and all their derivatives are functions of t, so you should keep that in mind when you're differentiating these. So, here's the pseudocode for a program that generates and prints a numerical solution from 0 to 1 in 100 steps. We've used the terms up to H4 in this particular series, but this will solve the original set of equations that we had specified. We can also write our original system of differential equations in vector notation, like you see in the first bullet point. This first bullet point is a special case of a more general problem. X prime is equal to f of t comma x, where x of a is equal to s, and x is equal to xy, and x prime is equal to x prime y prime. F is the vector whose two components are given by the right-hand sides, and we write f of t comma capital X because capital F depends on both t and capital X. We can continue this idea to handle a system of ordinary differential equations. First off, we write them in the following format. X prime is equal to some function f1 involving t x1, x2 to xn, all the way to xn is equal to fn involving variables t, x1, x2, all the way out to xn. And we provide a set of initial conditions in the last line, and here we set vectors x, x prime, f, and s. And now we have our ordinary differential equation written in a vector form. The M-ordered Taylor series method for this vector form is written as you can see on this slide, with x is equal to x of t, x prime is equal to x prime of t, x double prime is x double prime of t, and x triple prime is equal to x triple prime of t. We can now construct the pseudocode for the Taylor series of order 4 applied to the example on the previous slide. And again, here is the pseudocode for the Taylor series of order 4 applied to the vector notation example. We accomplish this through a simple change of variables and the introduction of an array and an inner loop. Here, we've got a two-dimensional array, dij, which is used instead of all the different derivative variables. In fact, this and other methods in this chapter become easier to program if the computer language supports vector operations. We can also use the RungeKutta method, and let's take a look at that. The RungeKutta method extends from a single differential equation to systems of differential equations. The classic fourth-order RungeKutta method for a system of differential equations is given in the second bullet point. Now here, x is equal to x of t, and all the quantities are vectors within components. The only ones that are not are the variables t and h, which are single variables. And we can write a procedure to carry out the RungeKutta procedure or method for us. So here's the pseudocode for carrying out the RungeKutta procedure. It's assumed that the system to be solved is in vector notation form and that there are n equations in the system. The user will furnish the initial value of t, the initial value of the vector x, the step size h, and the number of steps to be taken, which is labeled as the variable in steps. So the procedure xp system is also needed, which evaluates the right-hand side of the vector notation system for a given value of the array x sub I, and stores the result in the array fi. The name XP System 2 is chosen as an abbreviation for X prime for a system. And to go along with that, the RungeKutta method, we need a driver program, and this driver program here tests the RungeKutta system for the vector notation. And this does need to be rewritten in vector notation, or the original one does, and the slide shows a suitable main program for computing the right-hand side. What we can do is we can take the Taylor series, RungeKutta, and the analytic solution, and we can compare them. And as a numerical experiment for solving that particular equation, we obtain the following results. Here, both methods seem to work well compared with the analytical solution, and the results obtained using mathematical software. So I think for all of them, they're accurate to 5 decimal places, which is pretty good results. Perhaps not good enough to build bridges or to fire rockets, but pretty good nonetheless for something we can program fairly quickly. When we wrote the system of differential equations in vector form, capital X prime is equal to f of t comma capital X, we assumed that the variable t was explicitly separated from the other variables. It's not necessary to do this. We can introduce a new variable x0 that is t in disguise and add a new differential equation x0 prime is equal to 1. A new initial condition x0 of a is equal to a must also be provided. And basically what we do is we increase the number of differential equations from n to n plus 1 and obtain a system written in a more elegant form, where x prime is equal to f of capital X and x of a is equal to s. So consider again the system that we started with, the coupled system. X prime of t is equal to x of t minus y of t plus 2t minus t squared minus t cubed, and y prime of t is equal to x of t plus y of t minus 4t squared plus t cubed. And we have our initial conditions: x0 is equal to 1 and y0 is equal to 0. We can write it as a system with three variables by letting x0 equal t, x1 equal x, and x2 equal y. And so we can get this in our linear system of equations format, and we have x0 prime, x1 prime, x2 prime, and is equal to 1, and then x1 minus x2 plus 2x0 minus x0 squared minus x0 cubed plus x1, or the third line is x1 plus x2 minus 4x0 squared minus x0 cubed. And we have our initial condition, capital X0 is equal to 0, 1, 0 transposed. As a result of the preceding remarks, we can sacrifice no generality in considering a system of n plus 1 first-order differential equations written in the following manner. We can then write this system in general vector notation. System of differential equations without the variable t explicitly present is said to be an autonomous system. Numerical methods that we discussed do not require that x0 equals t, or f0 equals 1, or s0 is equal to a. But we can use the classical fourth-order Runge-Kutta method to solve these formulas. And the fourth-order method is given on this slide. Here, capital X is equal to capital X of t, and all quantities are vectors with the n plus 1 components, except for the single variable h. We can take a look at the pseudocode for this. Now, we do need to modify the procedure RK for system 1 by beginning the arrays with 0 rather than 1 and omitting the variable t. We call the resulting program RK for system 2. The driver programs that solve the example system are shown on this slide. And it's a typical ordinary differential equation solver, such as those found in mathematical software libraries. The user interfaces with them by writing a subprogram in a non-autonomous format. In other words, the ordinary differential equation solver takes as input both the independent variable and dependent variable and returns values for the right-hand side to the ordinary differential equation. Consequently, the non-autonomous programming convention may seem more natural to those who are using these software packages. We can also deal with higher order differential equations. So consider the initial value problem for ordinary differential equations with an order higher than 1. It means we're going to have something more than the first derivative defining this. A differential equation of order n is normally accompanied by n auxiliary conditions in order to get a unique curve as an answer. This many initial conditions are needed to specify the solution of the differential equation precisely, assuming that you have certain smoothness criterion that are present. So, for example, consider x double prime of t is equal to minus 3 cosine squared of t plus 2, and we have the initial conditions x of 0 is equal to 0, x prime of 0 is equal to 0. The general analytic solution to this is given in the last bullet. Here C1 and C2 are arbitrary constants. To select one specific solution, C1 and C2 must be fixed, and two initial conditions allow this to be done. With the two initial conditions, we have x0 is equal to 0 and x prime of 0 is equal to 0. Then that results in C2 is equal to minus 3/8 and C1 is equal to 0. In general, higher order problems can be much more complicated than this simple example, because this example has a nice property that the function on the right-hand side of the differential equation does not involve x. The most general form of ordinary differential equations with initial conditions that we consider are in the following format. Now, to solve this system numerically, what we need to do is turn it into a system of first-order differential equations by defining x1, x2, and xn as follows. x1 is x, x2 is x prime, x3 is x double prime, xn minus 1 is equal to the n minus 2 derivative of x, and xn is equal to the n minus first derivative of x. So whenever a problem needs to be transformed by introducing new variables, it's recommended that you keep a dictionary to show the relationship between the new and the old variables. That way you can transform them back and forth. At the same time, this information, together with differential equations and the initial values, can be displayed in a chart. Such systemic bookkeeping can be helpful in a complicated situation. So take a look at an example. So consider this initial value problem. X triple prime is equal to cosine x plus sine of x prime minus e raised to the x double prime plus t squared. Whew, boy, that's a mouthful. What we can do is we can make a chart that summarizes the transform problem. So the old variable is x, new one is x1. Old variable x prime, new variable x2. Old variable x double prime, new variable x3. And we can set initial values for them and differential equations for them. And then we get a corresponding first order system, which can actually be solved. Now consider this example here, where we have two higher order differential equations. So we actually have a system of higher order differential equations, not one. Here, because we have x double prime and y triple prime, we're going to need 5 different substitutions, but we do the same thing. We use a chart and transform the equation using the 5 new variables x1 through x5. And as a result, we can get the following first order system of differential equations. X prime is equal to this vector with the initial condition vector. We can also do similar work with autonomous systems of ordinary differential equations. So next time we're going to take a look at Adams, Bashforth, Moulton methods for dealing with ordinary differential equations, and at this point you've probably OD'd on ODEs, but there's just one section left.